Can you hear me okay?
Yes, great.
Hello, everyone. This is this is Sri Banerjee, and I am thank you for inviting me to this talk, the Hopkins GIS Day. It's always great to come in and talk at your alma mater. I graduated from the MAS program with geospatial and public health a couple of years ago. And overall, I have about 20 years of experience in public health, trained physician. So this talk is about a certain type of regression analysis. Keep using geospatial considerations in mind. So in this talk, what I will be doing is going over some comparisons between a traditional ordinary least squares regression, linear regression versus spatial models. And then also demonstrate some of the impact that geography has on lung cancer mortality rates. So the main dependent variable that is being focused on in this portion is talking about lung cancer, aggregate lung cancer mortality rates at the county level through FIPS codes, things like that. So I'll show how the comparison was kind of made, and also describe, finally, I'll end with describing how the model choice can have an impact in how policy is created. Next slide, please. Okay, so this is kind of a busy slide, a lot going on, so I apologize for that in advance, but on the left, you can see these are the lung cancer mortality rates, deaths per 100,000, so population is already taken into consideration. And as you can see, kind of in the center of the country, over in the Midwest and or so, there's a lot higher death rates than say in California or the Western region. So there's definitely something going on here. So more formally, let me also explain what was going in the model so that you know what variables were placed in there and what these numbers mean on the right. So models 2 and models 3, that's what I'll be explaining. So the main focus was to try to determine what environmental factors are associated more so with lung cancer mortality. Specifically, what environmental factors did I look at? Well, one of them was fine particulate matter. These are inhalable particles, and they have been linked to quite a few diseases out there. So that's why lung cancer would be a logical end result because of this. So a lot of these particles, they're in the atmosphere, chemicals such as sulfur dioxide, nitrogen oxide, these are pollutants that are emitted from power plants, things like that, which is why that was a logical variable to incorporate. The other variable that I wanted to take a look at is the number of days that the county has experienced or the zip code has experienced a heat wave. And so the number of days related to that, so that is more looking at global warming types of variables. So these are the two main variables. And a third socio-demographic factor was incorporated in terms of percentage poverty rate. So these were the three main variables. First thing that was run is a global model, the ordinary least squares regression, the results of which I did not have space to fit on here, but indicated that there was a significant relationship. However, when through Monte Carlo methods, there was a spatial variability test that was conducted as well. From this Monte Carlo, which by the way was a very computationally expensive sort of test to run. But after this was run, I was able to tell that there was, in fact, spatial variability going on. So the next step would have been, of course, to run a geographically weighted regression model. These are the results. The first column is actually mean, not standardized beta. Then the standard deviation, minimum, median, maximum. And this was a Python callable program that was used in order to run this. The third one, model 3, is actually a multi-scale GWR test. So this is a regression analysis which goes a little bit beyond the GWR because it captures under the assumption, GWR has the assumption that all relationships vary at the same spatial scale across all covariates. But MGWR, why it is significant is that it's an improvement because it relaxes that same spatial scale assumption and allows covariate specific bandwidths to be optimized. So MGWR is calibrated with a backfitting algorithm, which was introduced by Frothingham. Next slide, please. So here's where the comparison really takes place. The Akaike information criterion is a wonderful tool to be comparing models. So the global scale at the bottom, and I'm referring to the bottom of the slide. So the global scale has a pretty high AIC number, 6871. As model 2 performs better than model 1, and of course adjusted R squareds were compared as well, and we saw the same thing. I saw the same thing. And then model 3, the multi-scale GWR model, is even better. So the main theme that is coming out of this talk, this part of the talk, is the fact that model 3 performed the best. And so the fine particulate matter, the more fine particulate matter, the higher rates of lung cancer deaths, and then number of days in heat wave, higher lung cancer mortality. So that concludes my talk. Thank you for listening.
Great, thanks so much. I have a question. Did you use Markov chain for that Monte Carlo?
Yeah, right. So it was an iterative process, and I took 1,000 repetitions. So it took about 2 hours to run. So yeah.
And I guess I have another. Oh, we have another one here. Were models evaluated based on prediction, or would that be something to also consider?
Yeah, right, Frank. That was a really good question, and it's always good to see you on these talks. So yeah, definitely that the prediction, the predictability is something else. AIC is a pretty robust way to compare, but that would be something else to keep in mind. Thanks.
All right, thank you.
And smoking prevalence is something else that probably should be considered as well. Thanks for that suggestion, Madeline.